Hi folks, this is CEO speaking again. We're going one step further with our TTL circuits. Two things to recall from our previous logic circuits video, the number 4. The first thing to recall is this one. Inside the box, so inside this little box, there are 6 diagrams, identical diagrams, each of them representing one inverter. Why 6? Is because since these packages were first designed, the logic circuits, the TTL, they were designed in packages with at least 14 terminals. So if you remove the 2 terminals for the power, one for the power supply and the other one for the ground, out of 14, you remain with 12. And because one inverter only requires 2 wires, one input, one output, so 12 divided by 2, 6 inverters are going to fit inside. But as you also recall, these diagrams, if you have to draw them in any of your schematics, they are too cumbersome. So the engineers decided to have a symbol for the whole diagram representing the inverter. So we said that having the package again, these 2 is for the ground, so it won't count. This was for the power supply, you won't count either. So here we're going to have the triangle representing the amplifier and the bubble at the output representing the actual out of phase 180 degrees between input and output, the input being connected to the pin 1 and the output to the pin 2. That's for the first inverter. There is a second one right here, similarly connected, input to the pin 3, output to the pin 4. Of course, is going to be a third one right here, input pin 5, output pin 6, and so on. We go on the other side. They're going to be connected, input on 9, output on 8. The 5th one is right here, input on 11, output on 10, and the last one, the 6th, is going to be right here, input on 13, output on 12. So this is actually what's inside the package, okay? 6 inverters. Now, this is the first thing to recall, okay? And all are inside that little thing. The second thing to recall was a table we've made. I'm gonna make it bigger, figuring the 2 states of logic circuits. The 2 states, like a switch going off or on. And you can use any pair of words, if you recall that, which are opposite to each other. Like we can say true or false, or only the first letter, T and F, where you can say low and high, or L-O-H-I, or simply L and H. Either of them can be used. Negative and positive. Do not forget the mathematical values 0 and 1. Be very careful because that 0 is not 0 volts, is 0 logic. This is not 1 volt, is 1 logic. Now, the power supply for these packages is 5 volts. So power supply is 5 volts. And we expect, for the 0 logic, which is on the left column here, we expect that the low state to be 0 volts and the high state to be 5 volts. This is what we call the ideal situation. Okay? Or what's expected. Now, what happens in reality? I'm going to leave this one aside for a minute, and we're going to take some measurement. Right here, I have a package containing inverters already connected. And this LED here on my left the orange one, is connected over the input, and the other one is going to be green, is going to be connected to the output. So as you can see, when one is on, the other one is off. This is why it's called inverter, because the input and output are opposite to each other. And when I press that button here, the input goes 0 and the output goes 1. So 1 meaning it is on, okay? So 1 or 0, 1 the input, output 0, or input 0, the output 1. They are always opposite to each other. Now surely, as you can also recall, I was showing you some pictures on the oscilloscope, but not everybody has access to an oscilloscope. For that reason, what we're going to use to take measurements normally, we're going to just pick up a standard digital multimeter, and if I put it on the voltage, we should be able to measure some voltage. But take a look what happens. If I measure it here, for instance, this is going to be the input where the LED is connected right now, is about 2.7, 2.8 volts. It's not 5 volts. I connect to the output here, where is the other LED connected, is 0.37 volt. You see that? 0.30 something volts. And if I put it one pin further right here, take a look what you find. You're going to find something like 1.9 volt, 1.94. And if I put the next pin here, the measurement is 0.30 something again. So how do we judge these measurements? Because actually here is not a clean 0 volt, is not a clean 5 volt. Where do we expect the answers to come from? From the manufacturers. So what the manufacturers are saying? What are they saying is, if we take a look on the screen, I'm going to show you something here. So this is exactly the package we discussed before, containing the 6 inverters, okay? And the second picture is taken from Texas Instruments site. Remember, Texas Instruments is one of the 2 original companies having a patent for the invention of the integrated circuit. But what you find there is a kind of, I'm sorry to say that, is looking like gibberish. It's not, because these companies, all manufacturers, they always talk to trained technicians and engineers. But for the rest of us, how do you get out of this? So let's find out, what do we do, okay? So in order to understand these kind of measurements, I'm going to put all the others aside, and we're going to draw something here, okay? Let's suppose we have our inverter. So we pick up here an inverter, the input being here, input, and the output being here. So far so good? To simplify the whole thing, I'm not drawing the power supply, but you imagine, because the inverter is actually made of 4 transistors and a bunch of diodes and resistors, of course it needs energy. But here I was only drawing the input and the output to only judge the functioning or the logic of the whole thing. Now, we're going to drop an imaginary line separating the input side from the output side. Let's first connect. This is the voltmeter, the symbol for a voltmeter. Supposing this is the ground and this is the input, we connect the voltmeter between the input and the ground. And we want to take some measurements. Right here is the level for the 0 volt. And if you consider all this line up to here, that vertical line, this is going to represent the whole range of values between 0 and plus 5 volt. Simply because the states or the values you measure with the voltmeter, either the input or the output, they cannot overcome the value of the power supply, which is 5 volt. Somewhere here is 0.8 volt. And somewhere here is 2.0 volt. Now, because we talked about the real situations, you need a kind of tolerance when you take a measurement. So this is exactly what the manufacturer says. any manufacturer. Whatever you measure at the input, which is between 0 volt to 0.8, is going to be considered the logic 0 or the low state. So this is the actual tolerance. Anything between 0 to 0.8 volt is 0 logic. And everything which is above 2 volts up to 5 is going to be considered the logic 1 or the high state. What about, we measured before a voltage about 1.9 volt. Whatever is here between 0.8 volt and 2 volts is a kind of forbidden state. But you cannot prevent the circuit like we measured before to show you values in this range. And this, when you measure anything here between these two, bigger than 0.8 volt but lower than 2, this is considered a kind of confusing state. We call this the limbo state. Simply because it's not clear, it's confusing. When you measure anything here between 0.8 and 2 volts at any input of a logic circuit, a TTL, then you have troubleshooting to do because it's not 0, it's not 1. It's like you're in no man's land. Everybody's going to shut on you. Okay? So, here was our TTL circuit, TTL inverter. And what we are talking about now can be applied to any TTL circuit with a power supply 5 volts. Any of them at any input, they're going to respect that. Okay? So now let's move the voltmeter to the output. So we're going to connect the voltmeter right here. Voltmeter. Okay? We're going to have the same range of values. 0 volt here, and plus 5 volt here. Somewhere here, you're going to find 0.4 volt. And somewhere here, you're going to find 2.4. So for the output, the ranges for the tolerance are not the same as for the input, and there are very technical reasons for that. But today, we're just establishing what are these ranges, starting becoming familiar with them. So for the output, if you put a voltmeter at any output, remember we measure something like 0.38. Any between 0 to 0.4 at an output, this is considered the logic 0 or the low state. And anything bigger than 2.4, not 2 volts like for the input, 2.4 this time, up to 5 volts, is considered a logic 1. And if you put your voltmeter at the output and you measure anything between 0.4 to 2.4 volt, this is going to be the limbo state. So take a look. When you put both of them together right here, you're going to find exactly the picture. I'm going to show this one to you at the end. The picture the manufacturer gives you. Okay? But better for the understanding is to have a separate situation for input measurements and output measurements, because even if the range of values, they go between 0 volt to 5 volt, the tolerances when you take these measurements are not the same. Now, in order to identify all these values on the specs of the manufacturer, all these voltages establishing the ranges of measurements, they received some names. Here, when you talk about the logic 0 or the low state, we measure here at the input. So this is the VIL, the low input voltage. So the input voltage for the low state. This also represents the input voltage low. Both of them. But this one here, 0 volts, is the lowest possible value you can measure with a voltmeter. This is called a minimum, M-I-N, minimum. And this is called a maximum. So 0 volts is representing when the meter is connected to the input, VIL minimum. And 0.8 volts is representing VIL maximum. This is the maximum value you can measure and still consider at the input a low state. Similarly for the 2 volt and 5 volt. You are still measuring at the input, VI, but this time is not a low state, it's the high state. So the letter is H, VIH for both. And 2 volts is the minimum voltage considered good enough to be one logic. So this is the minimum, MIN, and this is the maximum. So here you have VIL minimum, VIL maximum, VIH minimum, and VIH maximum. We move on the other side because also these 4 values, they receive names. Now this time we measure the output. So we have here V output, that's not a 0, it's the letter O. V output low minimum, MIN, VOL minimum, VOL maximum, VOL maximum. Here is output voltage, still output voltage because the meter is connected to the output, but this is for the high state, so VOH. And the lowest possible value considered one logic is 2.4. This is the minimum, MIN, and this is the maximum, okay? So this is the actual situation when you take measurements. You should consider input and output on separate sides because the ranges for these logic states are not the same. Again, as a conclusion, what do they represent here? They represent a kind of tolerance of your measurements when you measure the input or you measure the output. And this is going to be, for today's video, the only document I'm going to put on Google Drive for a reminder, because when we're going to start measuring in real situations, we always refer to that piece of paper representing the tolerances of the measurements. And the last thing we do, if we move again to see what the manufacturer tells us, we are right here. And you are going to find all these values. Take a look. 0.4 is VOL. They didn't tell, but this is the VOL minimum. And 2.4 is VOH minimum. And you find all the values for inputs in black, 0, 0.8, and then in red 2 volt, okay? And then you find 0.4, 2.4, okay? And you find the names, the abbreviated names, okay? 1.5 is somewhere they put relatively in the middle for the limbo state, okay? And one last thing I may add here is for the output, somewhere here is a voltage about 3.5 to 3.7 volts. This is the average measurement for the one logic we expect the output to be measured for a circuit. We're going to find that soon when taking physical measurements, okay? So I think it's enough for today with these 2 things, okay? So thank you very much for watching and see you next time for more about logic circuits. Bye-bye.